So, good morning, everyone, or good evening, wherever you may be. It's Friday here or Saturday for you, wherever you may be. And we have a very interesting topic today, and it's all about exoplanets, the direct imaging of exoplanets. So I am really pleased to introduce to you Briley Lewis, and she is a National Student Foundation Fellow and the fifth-year graduate student at UCLA, studying astronomy and astrophysics. And Riley, welcome. And we're really looking forward to this.
Sounds good. All right, thanks for the introduction. Hi, everyone. Just like Christian said, my name is Briley. I'm a fifth-year graduate student at UCLA, and it's a National Science Foundation Fellow. So here in
Sorry,
the
science. Got that
no
one.
worries. The
Science,
NSF
yes.
funds a lot of the science
Yes,
here in the US. So I will share my screen and let's get started.
sure.
All right, so I want you to start off by imagining an exoplanet. So this is a planet far away around a different star other than our sun. So imagine one of these. What do you think of? What do you see when you really try to imagine it? I'll give you a second to think.
Would you like me to put the poll out? I'm not quite sure, or that's
Nope,
late.
nope,
That's
this
late.
is just
Okay,
imagining for
okay,
now.
good. Okay.
Okay, so hopefully you have a nice picture in your mind right now. What I would bet you see, well, unless you see nothing, like someone said in the chat, I would bet you imagine something like this, or maybe even one of the planets in our own solar system. And so this makes sense. We're more familiar with the planets in our solar system, and the headlines about exoplanet results that are in the news often show us artist renditions. So these pictures that you see here are all, ideas from artists where they made up something that could be what it looks like. But it's a pretty picture, not actual data. And these are also often based off of our solar system, since those are the planets we actually have a really clear view of. But what does an exoplanet actually look like through a telescope? And now here's where our first poll comes in. So question time, Christian will put up the poll. What do you think it looks like? Your options are, maybe it looks kind of like Saturn or Jupiter through a backyard telescope, where you can see some of the, stripes and the rings and everything. Maybe it looks like a fuzzy blob with some light and dark patches. Maybe it looks like just a couple of pixels in an image, or we can't see them at all. And I'm saying, what does it look like through a telescope if you were trying to just take a picture of the planet, not collecting fancy data like light curves?
Yeah, we'll give them a minute, and the poll's
Sounds
running.
good.
Yeah.
Ground-based or space-based doesn't matter. What do you think if we were to try to take a picture of an exoplanet?
Okay, we'll give a few more seconds, and then we'll share the results.
See a lot of people in the chat are thinking really hard about this one and thinking of all the ways we indirectly detect planets. But I mean, if we were to try to capture light from the planet itself. All right, we've got an interesting spread here. So we've got 11% say kind of like the planets in our solar system, like we see them through backyard telescopes. 14% of people say a fuzzy blob with some light and dark patches. 29% say a couple bright pixels in an image, and almost half say we can't see them at all. Well, I am super excited to prove you wrong and say that we actually can see them. So today I'm going
Here
to
we
tell you
go.
about
Okay.
how we image an exoplanet. And people who said a couple bright pixels in an image, you're spot on. So the picture here is real data. This is the HR8799 system, which has 4 planets in it labeled B, C, D, and E in this image. And so this is what we're going to go into today, how we actually get data like this. Someone in the chat said, maybe I could if I had a 10+ meter telescope with adaptive optics. You are on the right track there, my friend. So these pictures can be taken, but they are very technically difficult. And so why is it so hard? There are three main factors. One, we have an atmosphere that gets in the way. So the atmosphere of Earth, as you all probably know from observing, can get pretty lumpy, make your images blurry. That's a problem. And then the other thing that you can't get rid of just by going to space is that exoplanets are tiny and far away, which means they're really, really faint. And they orbit around stars, which are very bright. So you're trying to see a very faint thing next to a very bright thing. And so you can compare this to trying to take a picture of a firefly that is buzzing around the bright lights of Las Vegas and taking that picture from here in Los Angeles. So you can imagine that is a very difficult thing to do. So let's tackle each of these problems one by one and how we can deal with them with technology. But first, if it's so hard, why do we want to do this? You guys already brought up in the chat, you know, we have other ways of finding planets that we're really good at. So why are we trying to do this, firefly around the Las Vegas lights nonsense? And the answer is that other methods of finding exoplanets can't see the same ones that we can see with direct imaging. So right now, we're limited in technology by what each different method can find. So transits, where you have the planet block out some of the light from the star as it passes across. Transits are really good at seeing really close in big planets. So are radial velocities, where you see shifts in the planet's spectrum. And imaging is uniquely good at getting these, far out, very big planets. So the outer gas giants in a system. And the other thing is we want to see what planets are made of. So there's a couple ways of getting spectra, which can tell us about composition. And one of those is by doing direct imaging, where you're actually getting light from the planet itself. And the spectra we can get from direct imaging, can tell us about what the atmosphere is made of and more. And as this technology improves, it's what we hope will be able to tell us about habitability and signs of life on other planets. And the other cool thing about direct imaging is that we can actually watch the orbits of these planets. So unlike other methods where you have to disentangle these different signals, with direct imaging, you can just actually watch them move. So this is, again, the HR8799 system that we saw on the first slide. These are infrared images taken by the Keck telescope in Hawaii. And you can see how over the years that this system was observed, those planets are clearly moving in their orbits. So we can actually just watch where the 4 different planets are. So now that we've got some motivation, let's get back to how we actually can do all of this. So first, we're going to talk about the problem with Earth's atmosphere. Although now we do have some space-based observatories that can do direct imaging, like the James Webb Space Telescope, we're going to focus on direct imaging from the ground, because that's admittedly what I personally work on, and something that's going to be very useful in the next few decades. So the problem with Earth's atmosphere is turbulence. So what's going on in the atmosphere? We've got a distant object like a star with a planet around it. And as the light comes into the atmosphere, it's this nice flat plane wave of light. But then it hits the lumps of our atmosphere where there's different pockets of air at different temperatures, and they change the index of refraction of the light, so how much the light bends. And from this nice plane wave going through all those different lumps and bumps of temperature in the atmosphere, you end up with a wavefront of light that has all these bumps and wiggles in it. And that's what creates the blurry images that you see on a night with really bad seeing. So that's what's going on in the atmosphere, and we need to correct it. Someone already said adaptive optics. That's exactly what we use here on the ground to correct it nowadays. So for adaptive optics, that's how we fix these lumpy wavefronts. You've got an incoming wavefront with all those airs, and then a sensor that looks at that wavefront and tells a mirror how to move. And then that deformable mirror, so a mirror that can actually change the shape, corrects for those airs, and you get something at least kind of close to a fixed wave that's all nice and flat that then goes to your detectors. So we're basically correcting for all the airs of the atmosphere with this flexible mirror. And adaptive optics can do awesome things. I bet a lot of you know about this already, but adaptive optics gives us much, much, much sharper images. So this is an example from one of the groups here at UCLA that studies the galactic center with Keck. And it's a GIF that's flipping between what the galactic center looks like in infrared without adaptive optics. We can see it's very blurry. And then with adaptive optics, where you can resolve a bunch more stars than you could otherwise, and they're clearer, sharper points of light. This is a really big difference. And that's something we have to do in order to be able to have crisp enough images to see those tiny faint planets and resolve them from their star. So adaptive optics, step one, works really well. We're pretty good at this nowadays. And so the next step is dealing with the starlight. So the star is bright, the planet is very faint. We call that having a high contrast between the two things. So what we use is a little tiny piece in the optics called a coronagraph. These were originally designed for use for the sun, where you would take this little sort of black dot, block out the sun, and then you'd be able to see the sun's fainter corona around it, like in this picture. You can kind of also think of this as if you're standing on a stage with really bright lights and you can't see the audience in front of you, if you put your hand up to block the lights, then you'll be able to see the fainter audience since the bright light isn't shining in your eyes. So it's the same principle. And coronagraphs are extremely important in being able to image planets like this. So the picture on the screen here shows a simulation of what the solar system, our solar system, would look like to an observer 30 light years away from us. And on the left, there's what it would look like without a coronagraph, where all you see is the bright glare of the sun. And then with a perfect coronagraph, you'd be able to see things like Saturn and Jupiter clearly showing up as little dots. So blocking out the sun is the difference between seeing nothing and clearly seeing Saturn and Jupiter. So this is a huge part of our systems, is the coronagraph. And then we have to actually find the faint little planets in all of this. So this is what some of the data looks like from these kind of direct imaging systems here on the ground before we do all of our data processing. So one way of finding faint planets, and I think this GIF isn't working, this is supposed to be a GIF. So this should be a video where each frame is a different wavelength of light. And what you would see is those little speckles that make a square, those little dots, those will actually move out with wavelength. And that's just a feature like from diffraction of light. So just because at different wavelengths, the light is bouncing up the telescope a little bit different, your things move out. But planets and real objects out in space don't behave like that. They stay in the same spot. And so that's actually one of the ways that we can differentiate, okay, what is just a little dot of noise and what is a planet. This is called spectral differential imaging. There's a couple different ways that we can find faint planets in our data reductions besides this, but I'm not going to go into them right now. If you're curious, we can talk about that later. But so if we were to be able to see this moving, you would see that there's fairly clearly, once everything's moving, a little dot right here that stays still. So this is actually not a discovered planet. Hilariously, I say it's a companion because people thought it might be something, but it turns out it was actually a background star. But the point here is, in order to actually see faint planets, we need to do some kind of data processing. So we need to get rid of all the extra noise that is still left over after the adaptive optics and the coronagraph. And so when you take out the rest of those speckles, you get an image like this, where you can actually see, okay, there are real planets that were hidden in that noise. So what we do is we use the data itself to make a model of the noise and then subtract that from the image. So if you have an image that is signal plus noise and you subtract the noise, you should just have your signal after. And so if we make a model of these speckles, what we call speckle noise, and then subtract that out, we should get our planet signals. And that's what you see here. This is, again, a different view of the HR 8799 system we've been looking at so far. So there are definitely some limits to this technique, though, just like there are to the other techniques for finding exoplanets like transits and radial velocities. So everyone has their advantages, but everyone also has their limitations right now, which will hopefully, not be as strict as we improve technology. So right now, direct imaging can only find planets that are at large separations, so meaning they're far away from their stars. This is because the closer in you are to the star, the easier it is for the planet to get lost in the bright glare of the star. And also, if we're blocking out the star and something's right next to it, we might block out that very close-in planet with the coronagraph. So, oh, I see a question. I will answer that one. So, is there really a physical object in a coronagraph? How big would it be? If by physical object, do you mean like, is it actually like a little spot that is, blocking it out, like a physical thing? The answer is yes. It's so usually they're actually the masks are usually not actually just a black dot in the center where the star is. It's the opposite where it like reflects back everything besides the starlight, and there's actually just a hole in the center of a mirror. But they are actually about the size that I'm holding up with my hand right now for a lot of things. They're very small. Because what happens is you take, like the big beam of light from the telescope, and then you focus it down to go through the optics of your instrument. So they're not very big. They're pretty small, and the hole is even smaller. Absolutely tiny, tiny. So I hope that answers your question. So back to our limits and advantages. Our limits, we can only see planets that are far away from their stars because of that bright glare of the star closer in. And this is something that people are really actively working on, trying to improve how close we can see into the star with better instrumentation. Right now, we can also only see planets that are really large. So a bigger thing is going to emit more light, right? And so that is something that we're currently limited by because we need to see something bright enough to make it beyond that glare of the star. And again, this is something people are really working on, trying to find smaller, fainter planets so that we can image, a whole solar system instead of just the big outer ones. And then the other thing that's a really interesting caveat for exoplanet imaging is that the planets have to be young. So they have to have recently formed. And this means that they're really bright in the infrared. So most of the direct imaging we do, if not all, is infrared. So we are not looking in the visible light. We're not looking at light that is reflected from the star right now. We're looking at infrared light, the heat from a planet as it just recently formed. So when a planet forms, there's a bunch of things coalescing, and that leaves a lot of heat from all these things that have collided together to create a planet. And so when planets are young, they are actually what we call self-luminous. So they are emitting a lot of light themselves. And so right now, direct imaging generally looks for planets that are really young because those are the ones that are brighter, haven't cooled off yet. So that is another interesting limitation of this technique right now. I got a question of, can you please explain the third point? I think that's what I just explained. So I think you may have gotten a little ahead of me, but pretty much they must be young because they're brighter when they're young. So what have we found so far? We found 51 planets. I think this number has actually gone up to 52 or 53, but there's a little debate. It's around 50. We've also found some brown dwarfs, which I'll talk about what those are in a second. Some binary stars, so two stars orbiting each other, and then a lot of protoplanetary and debris disks, so the disks of gas and dust that are making planets. I've got a question again, I will answer that one. So if the planet is young and hot, doesn't that also mean there's probably still a lot of debris around the star? But wouldn't the debris interfere with the IR signal from the planets? Ooh, that's really interesting. And we're going to get to some pictures later that I think will tell you that. So we've seen a lot of planets where the debris has been cleared, but we've also seen ones where it hasn't. And I will show you some pictures of that later. All right, so Christian, can we put up our second question? So just out of curiosity, what would be the most exciting thing to find around another star to you? Would it be an exoplanet that looks like Earth, a black hole, another star like these binary stars, or something that's, technological that wouldn't occur in nature? Oh, I see in the chat an exomoon. That's a fun one.
Oh, this is going to be an interesting one. I'm curious to see how this pans out. What do you think,
Okay.
Briley?
So, that's actually about what I expected, honestly. So, Earth-like exoplanet, yeah, of course that would be exciting. That might have life. Um, a space station or something technology, that would also mean, there must be something that created it. Um, and then a couple people are interested in a black hole. I think that would be really cool. Like it would be weird. Like, how did this black hole get to be orbiting this little star? Um, and then another star. So I guess we're not very interested in binary stars here. But they can actually, they're very interesting scientifically. So we still try to find them when we can. Okay. So these are the things we found. And if you're ever curious about getting a very up-to-date count, you can go to NASA's Exoplanet Archive. So I put the link up here. This is how you can check up on the number of planets we've discovered. And they even sort it by what method they were discovered with. So right now it says 61 planets with imaging. But again, some of them are kind of debated still. I know this is a little small. I tried to get a screenshot just to give you an idea of what this looks like. And so right now we have discovered, and I pulled this picture yesterday. So as of yesterday, we've discovered 5,211 exoplanets, and a lot of those were from the Kepler and TESS missions, but only around 50 to 60 with imaging. So yeah, definitely go check up on this number if you're ever interested. Um, Someone asked the question, it's hard to see the planet. How would you see a space station? We wouldn't yet, really. This was more of a fun, let's imagine if we could find everything, what would you be excited about question. So that we would have to have a lot, more advanced technology to see something like that. All right. So back to what have we found? So we'll get to the planets in a little bit, but what about these brown dwarfs? Those are something that, I think some people might not know about. Why are they cool? What are they? Um, So, what's a brown dwarf, anyways? A brown dwarf is something that is between the mass of the biggest planets and the smallest stars. So, here you can see the sun compared to a red dwarf, the smallest kind of star. And then there's three different brown dwarfs that are between the mass of that star and Jupiter. And so these little in between things, some people call them failed stars because they never actually ignited hydrogen to helium fusion to make them burn bright like stars do. But I don't think that's quite right. They are these weird in between. So why should we care about them? Because they can help us answer questions about sort of what's the difference between forming a big planet like Jupiter and what's the difference between forming a big planet like Jupiter and forming a full-on star. Um, and because they're, you know, bigger and brighter than Jupiter and therefore easier to see, they can help us start to answer questions about how planets evolve and what's going on in exoplanet atmospheres because it's easier to see their atmospheres than it is to see Jupiter, but we think they have a lot in common. So we look at brown dwarfs to try and get an idea of, how these different things form and also what the atmospheric like chemistry and motion and stuff like that is for a big, ball of gas. I've got a couple questions I'll answer real quick. Someone says there's a long list of potentially habitable exoplanets, but which exoplanet is most promising? I don't feel like I can answer that yet. I don't think we have enough information. So the hope is that with, new telescopes like JWST and upcoming telescopes like Roman, and then eventually, um, it used to be known as LUVAR. Now people kind of call it LUVEX for reasons I'll get into a little later. So upcoming telescopes will hopefully be able to actually show us some biosignatures, and therefore we will have a better idea of which one is a good candidate for life. And a question in the chat was, um, let's see, are there really different worlds and different galaxies that are like the same as ours? Um, and so to be clear, when we're talking about exoplanets, we have only found exoplanets within our galaxy so far, with the exception of a couple maybes from like microlensing and stuff, I think. But as far as transits, radial velocities, and direct imaging, we are only looking at actually our very close by neighborhood, because further away, we can't see that yet, because the planets are just too small and too faint. But from everything we know, there's no reason that planets like ours shouldn't form around other stars. It formed here. Um, for all we know, life could be a really common process that happens in the universe. So what we're going to do now is we're going to go on a little tour of a couple of the discoveries from direct imaging. So let's move on to our first one. So this is 51 Eridani b. This is the lowest mass planet that we've found from imaging. So it's 2 times the size of Jupiter. And you can see in this image that we actually can see some of its orbit. So what we're going to do in this bit is I'll tell you about one of the discoveries and then show you the telescope and instrument that actually made it. So 51 Eridani b is currently our record holder for the lowest mass imaged planet, and hopefully we will break this record soon. And this one was discovered with the Gemini Planet Imager. So this was an instrument for the telescope that was, dedicated specifically to planet finding. That is what it was designed for. And it used to be on the Gemini South Observatory in Chile. And now the instrument has actually been taken off the telescope and shipped back up here to the US, where the Gemini Planet Imager team is upgrading it and will soon put it on the Gemini North Telescope in Hawaii. Since you guys are observers, you probably know you can see a different set of stars in the south than you can in the north. So Gemini did a survey of stars looking for planets in the south, and now the Gemini Planet Imager will hopefully do something similar in the north with an upgraded, bigger, better, everything instrument. This is one we looked at already today. So this was our title slide image, HR 8799. So A is the star itself, and then B, C, D, B, C, D, and E. I should have said B through E, not A through D. Yeah, so B, C, D, and E are the planets. So each of these planets that you see, each dot is multiple times the mass of Jupiter. And they are double the distances of Jupiter, Saturn, Uranus, and Neptune, respectively. So this is kind of like a big scaled up version of our outer solar system. And it's one of the best studied directly imaged systems. You can see based on the timestamps here that we've been observing this for a long time, and still are, to try to get more information about this system so we can really understand it. And that photo was taken with the Keck Observatory. So this is a major observatory in Hawaii with famous 10-meter telescopes and a lot of different instruments that can be used to investigate planets. Oh, we got a question. Is the adaptive optics in the imager or in the telescope? So it is part of the telescope facility, but does, work with the instrument, if that makes sense. So adaptive optics are a feature of the facilities. Like Keck has its adaptive optics system where you can use the laser guide star, which let's see, it's not in this image, but sometimes you'll see images of the Keck telescopes with like a laser pointing into the sky to represent the adaptive optics system, or you can just use it on a star without using the laser. Another question, how far away is the farthest star with an exoplanet that you can directly visualize? And I don't actually know that number off the top of my head. It's not that far. So if you were to draw a picture of our Milky Way, and where our sun is out on one of the arms, the dot is very, very small. We are not seeing a large fraction of our Milky Way. Another person asks, what were the circular flashes in the movies? I'm not sure what you mean by circular flashes. If you mean right around the center. So the center is right where we've blocked out the star, and all that's happening around the center is a little bit of light getting around that coronagraph from the star. So that's why anything that's right up against where we block out the star, that's why it would be so hard to see a planet there, because the starlight is still getting through. So those, if you're talking about the circular flashes in the center, that's what it is. Okay, so HR 8799. Our next one is Kappa Andromedae b. So this is a planet so big that it could actually be a brown dwarf, maybe. People have found out that it's 13 Jupiter masses, which is right on the borderline of what we define as a planet versus a brown dwarf. Um, so it's interesting because it's helping us probe sort of that difference between these two categories. And this one was found by the Subaru telescope, which is also on Mauna Kea, um, and has a really cutting edge adaptive optics system called SKEXAO. And so on the right here, you can see a picture of a star where the star is blocked out without SKEXAO helping, and then with it helping. So it really helps get rid of more of that starlight. And this is a telescope that's run by the National Astronomical Observatories of Japan. And now we're on to not just planets, but also disks. So that dusty stuff that someone mentioned in a question earlier. So Beta Pictoris b is this really interesting system where we have seen both a planet and a debris disk. So all of the dust left over from forming planets. So the, yellow, red, and blue on the outside, that is the debris disk. And that's overlaid on a directly image or an image of directly imaging the exoplanet Beta Pic b. So Beta Pic b is about the orbit of Saturn. And we can see, we've actually seen it orbit on both sides of the star. So we've seen that it is edge on aligned to us basically, and it's orbiting back and forth. So the picture on the right is the back and forth. Got some more questions. Have we direct imaged exoplanets yet where the orbital axis is far from our line of sight? I'm not sure what you mean. We've seen both systems where it's edge on, like in Beta Pic, and then closer to face on, like we saw in HR 8799. And then we've got, can a study of the motion of the directly imaged exoplanet through any light, show any light on the probable existence of a smaller exoplanet nearby? I don't think anyone's really done that yet. People have done the opposite, where you are looking at transits or RVs and noticing a signal that shows there might be something far away that is kind of, jostling around the smaller inner planet. But I don't know if anyone's done it the other way around. So Beta Pic b has been imaged by a bunch of different things. One of the telescopes is the Very Large Telescopes. So these are two 4.8-meter telescopes run by the European Southern Observatories that are located in Chile. And they can actually be used together. So these four telescopes can be used together to act as one larger telescope. And someone asks, what could be the reason for the warped disk, the right part of Beta Pic? And so warps and disks are generally caused by planets, either seen or unseen, moving around that dust and kind of contorting it. So if we see a warped disk, but we don't see a planet, it can actually be an indication that there may be a planet hiding from us. All right, and now a debris disk where we don't really see a planet. So the difference between a protoplanetary disk and a debris disk is that a protoplanetary disk is younger. It's the earlier stages of planet formation, where there's still a lot of gas around in addition to the dust. But a debris disk is really just dust at that point. It's sort of the elderly planet forming disk. So this is HR 4796. It's a debris disk known as the Eye of Sauron for, I think, obvious reasons if you've seen Lord of the Rings. And it's really interesting that we can see this ring of dust. So an analog to this in our own solar system is our Kuiper belt, where we've got a belt of rocky icy debris that is orbiting, on the edges of our solar system. And then another debris disk known as the Eye of Sauron, because apparently those things just look like this, is Fomalhaut and Fomalhaut b. This one actually has, we think, a forming planet in it. So you can see Fomalhaut's, very big, very debris disk here. And on this little inset, you can see the planet Fomalhaut b. For a while, it was unclear if it was actually like a planet or if it was just a weird clump of dust that wasn't really yet a planet. But it's been observed multiple times moving actually in this disk. And then someone asked, what if there's dust getting in the way? Like, what if, it's a really young system? And the answer to that is PDS-70b. So this is an absolute baby planetary system. So you've still got this protoplanetary disk around it and this forming planet that's here, this big lump in the center. You can actually see two little sort of wisps around it as material is, like accreting onto that forming planetary system. So it's time for our third question. So Christian, our question time is, which of these discoveries do you find the most interesting? Is it 51 Eridani b, the almost Jupiter-like exoplanet, HR 8799 b through d, the multiple planets that we've imaged, Kappa Andromedae b, the big, almost a brown dwarf, Beta Pic b, the disk that has a planet inside, HR 4796, that's the thin ring of rocky debris, or this one, PDS-70b, the baby planet just being formed.
Yeah, whilst they answer, I can quickly throw in a question. I find the nomenclature so curious here because, for quasars also, we have a very set, a right ascension declination nomenclature. How do they come up with these weird names?
Yeah, so the way that exoplanets are named is just after the star that they are around. So it depends on what catalog they used to identify the star. So HR, I forgot what the HR catalog stands for. A lot of them are HD, which is the Henry Draper catalog. Some of them, the brighter stars, are named. So like 51 Eridani is a star in that constellation. Same with Kappa Andromedae, that's, a star in the constellation Andromeda. Beta Pictoris, similar thing. And then the others are just different star catalogs that people use to reference. And then the planets are always B, C, D, and so on based on the order that they were discovered.
Thank you. That makes sense. Thank you.
Yeah, people often ask, if you find an exoplanet, do you get to name it? And the answer is, unfortunately, no. It's really just these numbers. So, we've got a lot of love for HR 8799 and PDS-70b. Close second there by Beta Pic, and then I think 51 Eridani b, Kappa and HR 4796 are kind of tied for last here, but still got some votes. I personally think these are all really cool discoveries because they all show us very different things about the diversity of planets outside of our solar system. Before we move on, I've got a question. Was the Fomalhaut image visible light? No, these are all infrared. All of the direct imaging stuff I've showed you is infrared. And so what comes next? We've seen some of these discoveries. We know we want to see smaller planets, fainter planets, be able to see them in more detail. So there's really two ways forward. One is new space-based telescopes, because going to space gets us away from that pesky atmosphere, makes that just a non-issue to deal with. And then the second is new, bigger ground-based telescopes and instruments, because bigger telescopes give us better resolving power to see faint things. So some exciting space missions. One, obviously, the James Webb Space Telescope launched Christmas Day last year. This has been doing lots of cool science all year. So it does have some planet finding capabilities. This telescope's much bigger than Hubble. It's got a 6.5 meter mirror. It's looking in the infrared, both the near infrared and the mid infrared, so longer wavelengths. And this is good for dust, which is obviously relevant for planets, and then also far away, like redshifted or earlier in the universe things, which not quite as interesting for us planet folks, but cool for science nonetheless. And the big exciting science, the thing that JWST is like really good at is transit spectroscopy. So someone mentioned earlier about transits, how you can actually see the light curves. And transit spectroscopy means you get light curves in different wavelengths, and you can use those to figure out where more light is being absorbed by the planet, and kind of back out a spectrum. But there are also some instruments that have coronagraphs for imaging. And so two of the really exciting exoplanet results from JWST so far, one was released in the first images in July. So this you may have seen in press conferences. This is actually one of those transit spectra. So the enormous mirror of this telescope, along with the precise instruments, made it so that we could actually get detailed measurements of starlight filtering through the atmosphere of a planet outside of our solar system. And so this has the information about what's in that planet's atmosphere and has showed evidence of clouds and haze that previous studies of this planet weren't able to detect because we just didn't have the precision yet. I see a couple questions. I'll answer those real quick. Are most of the exoplanet solar systems similar to the solar system we live in? Is there any known exoplanet which has the possibility to have life or similarities with Earth? The answer to the first bit, no, they are not mostly similar to us. Planetary systems are so much more diverse than what we would have thought. Like there are tons that look nothing like our solar system and have types of planets we just don't have here. And again, like I said earlier, we don't really have enough information to say confidently, yeah, this exoplanet, like, we think it has a good chance of having life. Right now, we mostly have this planet could be at the right temperature for water, and that's about the best we have. It's also got how big does the star have to be for a planet to orbit around it? Any of the stars, all of the stars. Things can orbit around any other thing with mass. So like even in the solar system, we've got binary asteroids. So lots of things, anything with mass can orbit another thing with mass. And then just wondering, how many directly imaged exoplanets have atmospheric compositions close to our Earth? The answer is 0 because we're only really imaging gas giants right now. We don't yet have the technology to actually image Earth-like planets. So there have been, or actually I don't think there even have been some with transit spectroscopy that have looked Earth-like. But that's because this is really a technique that's like just, we're in the beginnings of this technique and in a really exciting time to start getting results soon, like this from J2ST. And so there's probably a lot more to come there. And an image that got a little less press attention. So this is J2ST's first directly imaged planet. So around this star, it took images in 4 different wavelengths of the same planet. And so this is like the most precise spectrum we've gotten of a directly imaged planet so far. You can super clearly see it. It's really awesome and proof that these instruments are working. So this wasn't a new discovery. It was an exoplanet we already knew about, but they wanted to use it to test how well J2ST could work on actually, taking data on these systems. Another exciting one, W1st, now known as the Nancy Grace Roman Space Telescope. This guy's launching in probably the mid-2020s, which we are rapidly approaching. And NGRST is going to have a coronagraph. So this telescope is the same size as Hubble, but it's going to have something that's like really dedicated to finding planets. So we call it, it was called W1st at first because it has a wide field. So its field of view would be 100 times larger than Hubble's. And with its coronagraph, we'll hopefully see planets 1 billion times fainter than their stars. For context, Earth is 10 billion times fainter than our sun. And right now, we're seeing planets that are around 1 million times fainter. So this is a big improvement, not quite all the way to Earth-like planets, but definitely a big improvement. And so there's also some exciting ideas for space missions. So one is the idea of LUVOIR. So I say a version of it sort of for reasons I'll get into in a second. But so LUVOIR was this idea where people were like, let's just make a gigantic telescope, like obscenely large. So for comparison, you've got the small circular mirror of Hubble, the mirror of J2ST that we think is huge because it's 6.5 meters, and then the original proposal for LUVOIR was this 16-meter behemoth next to it. So this would be a wild thing if we could make it work. And this mission concept considered itself like the next Hubble. So looking at many different wavelengths, unlike James Webb, which is focusing on the infrared. The original plan was a 15-meter mirror, or there was a plan B with 8 meters. And the plan was to have a coronagraph with a goal to find Earth-like exoplanets. And a bonus, it could do some really cool solar system stuff. So these two on the right are not real data. They are simulations of what LUVOIR should be able to detect if, it was designed and actually created as planned. And you can see it would actually be able to image Earth-like exoplanets. And it would be able to give us these absolutely wild images of things in the solar system. Like this would be Enceladus with its little water plumes. And another one that is, a version sort of this idea might be launching in the 2030s is HabEx. So this was an idea for a mission where you had 2 things orbiting independently of each other, but doing it together, so co-orbiting, where you've got this big star shade that acts as the coronagraph, and then you've got the little spacecraft that actually has the telescope in it. And something that's really cool is that HabEx would have been just its only purpose would have been planet finding. It would have been a fairly small telescope, but the technology that would have been the really big development was the coronagraph itself. There'd be a coronagraph within the telescope and this star shade that unfolds like this cool piece of origami orbiting outside. And its goal, HabEx, was to find habitable Earth-like exoplanets. And the reason that I say that for both LUVOIR, a version of it sort of might be launching in the 2030s is because these were ideas proposed before something called the decadal survey. So every 10 years, there's the decadal survey where, oh, I see someone says their question is answered. I will miss that one. So every 10 years, the decadal survey is a process where astronomers say, here are the things that I think are really important for the field in the next decade. And they write papers and submit them to a committee of astronomers. And then that committee reads through all of the input from the community and helps determine like, okay, here are our recommendations for what is important for the coming decades. And LUVOIR and HabEx were two things that were submitted from the community to be considered as priorities for the next decade. And what the committee came up with was, what if we do a telescope that's sort of a mashup of the two of them? And so now people informally refer to it as LUVEX, just a combination of the two names. But something like that could hopefully be happening in the 2030s, 2040s. And of course, there are cool things happening here on the ground too. That's what I'm most invested in. So our current major planet finders are circled on this. We've got the Keck telescope and the Very Large Telescope on the bottom that we mentioned earlier, as well as Gemini South and the Magellan telescopes. And then these three big boys on the side, these are what are known as the extremely large telescopes. So these are the sort of next generation of telescopes that are, instead of 10, like a 10-meter across, they're 30 or more meters across, so tens of meters. So remember, bigger light bucket, fainter thing as we can see. So one of these projects is the 30-meter telescope, or TMT, which was originally planned to be completed in the late 2020s. This is a project that is a partnership between the US, India, China, Japan, and Canada, and is either going to be located on Mauna Kea in Hawaii or in the Canary Islands in Spain. One reason that I say it was originally planned for completion in the late 2020s is that there's been significant debate around where to put this telescope because of pushback from Native Hawaiians over the use of the sacred mountain Mauna Kea. So I want to acknowledge that there are these groups of Hawaiian land protectors at Mauna Kea that are fighting for indigenous rights. And this has been a very big conversation within astronomy and, with kind of how astronomy has been in the news in the last few years. So it's a very complicated situation. I totally encourage you to read up more into it. Don't have time to get into the details of it now, unfortunately. But there are two other extremely large telescope projects that are, still currently going forward. We've got the Extremely Large Telescope. This is the European Observatory's version. It would be located in Chile in the Atacama Desert, where we already have a lot of telescopes, and is planned to be completed in the next few years, hopefully. And then there's also the Giant Magellan Telescope, another one that would be in Chile. And the US does have a hand in this one too. The partners are the US, Australia, Brazil, and South Korea. And this one would also be hopefully done at the end of the decade. And then, of course, we're also always working on better technology for the telescopes we already have. So at Keck in Hawaii, for example, there's a new instrument that is, currently being developed and tested and I think just had first light called the Keck Planet Imager and Characterizer, or KPIC. And it's basically a new coronagraph that would help find more planets at Keck. I have a couple questions I will answer real quick. Someone says, how is radial velocity used to find exoplanets? We're not going to talk about that today just because that can be a whole other thing, and NASA has a really good website about it. Let's see, does NGRST have a much shorter focal length than Hubble, leading to the capable wide field? And how is the coronagraph working at such shorter wavelengths? So NGRST is also, I'm pretty sure, an infrared telescope. I don't know the details of the design of the telescope itself, unfortunately. I'm not really involved with that one. Let's see, since India is also part of this research, as you just told, is there any plan to install an ELT in Ladakh, India, where there are extremely clear skies? I have not heard of any plans to put a telescope in India. I know we usually put things on Mauna Kea and in Chile because they are really good conditions where there's not only clear skies, but it's also very dry, so that you don't have to deal with weather. And those two places are also very high, so you're past some of the atmosphere and you have to deal with less of it. So that's a really interesting suggestion, but I don't know. And then there's another question about tests, which I admittedly have no idea. I have not been keeping up with test news recently. So yeah, let's move on to the very last bit of this talk now that it's 10:52. So if there's something you take away, there's really a lot to look forward to in the coming decades when it comes to exoplanets, both through direct imaging and other methods. Like we have a lot of interesting telescopes coming up and lots of really cool things that, should happen soon. Like I think it's reasonable that we might detect biosignatures in all of our lifetime. And that would be cool to see signs of life on another planet.
And thank you for answering all those questions so efficiently.
Oh,
And
no
also,
worries. Like I said, I taught on Zoom for 2 whole years. I've gotten used to this.